In physics, tensors and general relativity are like inseparable brothers. Just as one brother supports the other, tensors form the mathematical backbone of general relativity, giving structure to its elegant equations. They are the pivotal force that forms the very essence of Einstein's field equations, describing the curvature of space-time caused by mass and energy. Without tensors, general relativity would be like a symphony without notes, a language without words. Together, they reveal the cosmos' deepest secrets, from black holes to the bending of light, illustrating a relationship where one is incomplete without the other. Welcome to the third episode in this series of How to Learn the Mathematics of General Relativity. In today's video, we are going to look into tensors, the most important, crucial, and foremost dominant concept that rules general relativity. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to episode 3 on how to learn mathematics for general relativity. Before I go ahead in the third episode, here is a quick recap on the second part in case you have missed. Although I have put it in a separate playlist and have created an I button through which you can check the entire playlist till now. So in the last video, we actually talked about linear algebra. And here are a few snapshots from that video. Why do you need linear algebra? As I tell that we often do mathematics without knowing the reasons. Similarly, in linear algebra, we do just for scoring good marks, etc. So in the last video, you learned about metric tensor, Ricci tensor, and different concepts which are very foundational in terms of relativity actually depends on linear algebra. You also looked into that the mathematics of linear algebra is actually a nice and an elegant way where all those equations are written easily. And we are going to look more into that in today's video. You also learned that various concepts of relativity, for example, vectors, length of a vector, diagonalization, and most importantly, the metric tensor and volume element actually depends upon linear algebra. So when we transit or we do an elegant exit from the familiar Euclidean space to the non-Euclidean space where things take a weird turn in terms of curvature, we find that general relativity and the linear algebra are intimately related to each other. We saw those concepts in the last video. As just this is a quick recap, the mathematics of linear algebra again helps to define and understand the concepts of relativity much easier. You also saw that in terms of non-mathematical way, there are various ways in which they are related. For example, if you do the diagonalization, linear transformation, and the symmetric tensor and the anti-symmetric tensors, these are all concepts which are actually taken care of linear algebra. So what is symmetric tensors, etc.? What is the feature of that, we will come to know. But in case that there is a transformation or we need a diagonalization of a matrix in order to cancel out some of the terms, etc., how can you do it without linear algebra? So we in the last video you also saw that some of the books, and I recommended this book, particularly Elementary Linear Algebra, due to certain reasons, because it is a very easy book. It actually gives you a nice transition from the general vector spaces to the abstract vector spaces. It is very cohesive. The proofs are presented in a nice and easy way, and there are other historical events which makes the learning more solid and interesting, and there are certain other things which were presented in the last video. So you see that there are certain graded exercises in that book, and also the student solution manual and the website was also given. So that is why I recommended that this would be the first book to start with linear algebra. You also saw that there are several books which were including Gilbert Stank's famous linear algebra, Schaum's outline, linear algebra done right, and so. And we also came to know that what the most important books, and most importantly a very detailed review of those books as well as a sequence in which you would read first, second, and third was given. So this was what we learned in the last video, I mean to say in terms of linear algebra. Now, this is something which you might have seen through your journey cruising through the mathematics of general relativity, that the metric tensor and the stress energy momentum tensor, etc., that comes up. and then we have something which is anti-symmetric tensor, which is called an electromagnetic field tensor. Now don't you see that all those matrices are something similar to that of the general linear algebra matrices? So the question is that these metric tensors, etc., resemble what is called a tensor. So what is a tensor and what is the pivotal role? Because as I told you, they are inseparable brothers. So how does it play a pivotal role in general relativity? Why is it very important? And most importantly, how to understand them? Because most of the students I have seen, they find tensors really very difficult. But I am going to make life super easy in this video. Now, before I go ahead in learning about tensors, I always do that there are certain misconceptions which comes up in terms of understanding a physics or mathematics concept. So first I would like to clear up those misconceptions, and then I would go step by step in making you understand about tensors and relativity. So as we turn the pages, what we first see is that generally people have an idea that tensors are just fancy matrices written in different way with indices, but it is not. Tensors are not just fancy matrices. So tensors do have certain transformation properties. These transformation properties are defined, and it is basically for how the coordinate changes, which is not a concept of regular matrices. So they are more general and carry n dimensions in terms of matrices. So matrices are actually limited maybe to 2 or 3 dimensions, but tensors can have any number of dimensions. So tensors are not just fancy matrices, but there are more than that which carries rules. The second misconception is that all multidimensional arrays are not tensors. Now what do I mean by that is that although it looks like multidimensional arrays, as you have seen that the stress energy tensors, etc., but they are not just multidimensional arrays. So tensors actually have to qualify, or I would say satisfy certain transformation rules. If they satisfy under transformation rules, then it can become this or it can become this. So it is not that all multidimensional arrays are not tensors. In order to qualify to become a tensor, there are certain parameters which you need to learn. Now, the third one is which most of the students think to be so, and I would like to destroy that myth, is that you really need to be a mathematical genius in order to learn tensors, which is absolutely not, which we will see in this video. That with the right approach and resources and with the core concepts of some of the mathematics that you need, for example linear algebra, etc., which we will come, tensors can be mastered very well. It is not that you have to be an absolutely math buff or a mathematical genius in order to do so. You just need to have certain concepts in your mind in order to learn tensors. And finally, tensors definitely are not only theoretical. If you have noticed my earlier videos, I have mentioned that it has got multiple and numerous practical applications. For example, Google's TensorFlow itself is a machine learning tool which includes the concepts of tensors, fluid dynamics, data science, machine learning, crystallography, lot of examples. So tensors definitely are not all theoretical. Having said this, the misconceptions you must have removed from your mind. Now we come ahead and define what is a tensor. Coming up into the next part of the video, we will look into understanding what is a tensor. As most of the terms are either taken from Latin or Greek, tensor is not an exception. The word comes from the Latin tender, which is to stretch. In anatomy also it is used as a muscle that tightens or strengthens a part of the body. So from Latin and from anatomy, what we can understand is that tensor has something to do with stretching or pulling or things apart. From there we can deduce that it has something to deal with stretching. So if I've got a sphere around here and if I stretch this sphere, it will become an oblate spheroid. So here is a kind of an information, any kind of an information, it could be physics, mathematics, economics, biology, whatever. So if this information is now getting stretched over there, the question comes that how will we come to know about that stretched information? So if the coordinate gets stretched up, the data should not be stretched up. Then how will we find up that data? So herein comes the question that tensors are something which stores some amount of information which is stretched, which is extended or deformed in various other geometrical sense. So we need a property, we need a mathematical tool in order to know that how we can denote those stretched information. So we can say that it is a set of components of the coordinates of any point that transform linearly between coordinate system. It is non-linear, it would have been a problem. So things which transform linearly from one part to another, it becomes easier. If you have watched my earlier video in the linear algebra of quantum mechanics, there's an underlying truth that things in quantum mechanics also transform linearly. And that is the reason linear algebra is used for that. So here also they transform linearly. Now this is something very, not very clear, but let me make you understand through some quick and beautiful diagrams. So if you've got a flat space, a Euclidean space, and you got this kind of a curvilinear space. So if I get an information which is marked in red, so if I now stretch it in this way, so the question is that we move from a flat to a curved space, because general relativity specifically is all about curved space. So the question rises that in here also we get an information which gets stretched over here. So the object is stretched. How do we measure that? So in a flat space, again, we take an analogy that we have got an information, something around here, and if I rotate that, the information from here would become here, because we have rotated. So the coordinate system is rotated or stretched whatsoever. So the question lies that how do we measure things and how to keep the measurement invariant in spite of coordinate changes. That means whether it is stretched, it is curvilinear, whether it is rotated or whatever. How do we keep the measurement invariant? Because the measurement is the ultimate motto of our physics. So here comes the ultimate idea that the laws of nature should be invariant, and that is where the tensors come into play. Let us look into another analogy to make things clear. Here is a person who is throwing a ball, and the same person is throwing a ball from here to here, but in this system the axis is rotated. So here also there is an event in the flat Euclidean space, and in the non-rotated and the rotated axis there is another event. So from here what we can say that events will be measured in the same way irrespective of whatever the frames are rotated. So here is another example. The same person who is throwing a ball, and the same person is throwing a ball, but in this case the axis is extended. So event from here also is coming to that event. So event will be measured in the same way in all frames of reference. This is the basic target. So the same analogy comes that a sphere has got something like this and an oblate spheroid, things get stretched. And that is what Albert Einstein told, that the general laws of nature must be expressed by identical equations relative to all other systems, whichever way they are moving. And that is why if you have gone through my history of general relativity, Einstein's strive was to find out a covariant theory of gravity. That means whatever happens with the coordinates, but the laws of the nature should be measured and it should be expressed by identical equations irrespective of whatever the way the coordinates are moving. And that is why Einstein strived to find out and ultimately was successful in finding a covariant theory of gravity where things are moving in accordance to the to the measurement. Now when we talk of tensors and Einsteins, obviously one thing comes into our mind which is called the Einstein field equations. Now, in numerous videos, at least 7 or 8 or 10 maybe in number right now, I have explained it, but those who are watching for the first time, I think this would be a right time to explain. Now, in this equation, you see something is on the left hand side, something on the right hand side. So both of them are equated by equal sign. That means this should be equal to this. Now, there are certain things which are constant, for example, lambda, which is called the cosmological constant. We know C4. I will tell you why it is 4 later. It is called the speed of light. We know what is an 8 pi. This is a constant, and the good old-fashioned gravitational constant G. So these are the things which are constant. Now we are worried about what are the things which are variable, and that we will look into the components of Einstein's field equation into the next part of our video. So these are already constants, as you understand. So with constants we are not worried about. What we are worried about is this R, which is called the Ricci curvature tensor, and it measures how the volume of a matter changes when it moves from flat space to curved space. Now I understand that this term or this statement is not okay with you, but don't worry, we will explain it in the video some part and in the coming videos. So remember that a volume actually changes from flat space to curved space, and this volume means the differential volume. Then comes this R, which is called the Ricci Scalar, which keeps track of how the size of a ball deviates from Euclidean space. Now, why we are taking a ball and not anything else, that we will come later, but this is how Ricci Scalar behaves. Now we come to 2G, and both of them are the same. They are called the metric tensor, the central and the most important component of Einstein field equation, which measures the causal structure of space-time. What do I mean by that? Maybe angles, distances, how far it is, just to make you understand. So the causal structure of space-time, just in Euclidean space, you measure how far it is, how near it is, what are the angles, what is the distance. It is similar to that in metric tensor. Then we come to something which is hidden, which is called the Riemann curvature tensor. It is actually a contraction of the Ricci and the Ricci curvature tensor and the scalar, but this is also described a kind of a, I would say, curvature. And finally, we look into this capital T, which is called the stressenergymomentumtensor, and it actually tells that how much matter movement can be registered through that tensor component. So the right hand side is totally on what is called the matter movement, and the left hand side is what is the curvature. So actually the matter tells how much to curve, and the curvature tells how the matter to move. I won't go into making those 16 equations, etc., which we will come, but this is what we mean to say what is a tensor, and the most important part is Einstein field equations is heavily dependent on only about tensors. Now when we talk about tensors, automatically the question comes, we saw anatomy, we saw the Latin word, that where from the origin of the tensors are coming. We will come to that, but before that, if you want to know anything about these field equations and delve deep into that, understanding each and every component, you can go to lesson 21 in my playlist of General Theory of Relativity. You will get a complete beginner's guide to Einstein field equation where I have explained each and every part. So now we begin to know that what is the origin of tensor. Don't worry, I don't go much into the history, but this is a quick learning because origin of tensors is something which will guide us to make our future endeavors in terms of learning. So the person, there are many people like Tullio Levi-Civita and Bernhard Riemann, but we owe our due gratitude and respect to this person, Dr. Woldemar Voigt. And as you can see that Woldemar Voigt was a German physicist who made significant contribution to the field of crystallography and solid-state physics. In his studies of the physical properties of crystals, particularly their elasticity, he introduced the concept of tensors. Now this is a German original version of this book, The Fundamental Properties of Crystals, and you can see I have underlined those German words where the word actually the tensor comes in. So as you understand that Voigt's primary research focus was on the properties of crystals, especially their elastic and optical properties. He aimed to understand how crystals deform under stress and how these deformations relate to their internal structure. So Voigt in this paper used tensors to describe the elastic properties of crystals, which require considering how forces and deformations are transmitted through different directions within the material. So this was one person, Dr. Woldemar Voigt, whose this paper actually marked some kind of a beginning, or on a very primitive level, the origin of tensors. The next person whom we get to come to know was an Irish mathematician by the name of William Rowan Hamilton. And he was a physicist and an astronomer who made significant contributions to classical mechanics, optics, and algebra. Now, he is particularly known for his development of this paper, which is called On Quaternions, or a New System of Algebra, and his influence to the mathematical concept of tensors. So in 1843, Hamilton introduced quaternions, a new mathematical system that extended complex numbers to 4 dimensions. So as you can see, I have again underlined those which are written now in English. Tensor, tensor, tensor. These are the terms which actually show. So quaternions consist of one real and other 3, I would say, imaginary part. So Hamiltonian mechanics reformulated classical mechanics, and this framework influenced the later development of tensor calculus, especially in the context of general relativity and what we call continuum mechanics. So there are other physicists. I won't take time to expand on that, but this was the origin. And as you saw that Woldemar Voigt was actually studying crystals, and I have explained in my other videos also that originally it started with the study of crystals. Now you see what happens when these crystals are actually heated, and their actual deformation have many faces and directions. So with vectors we can have a magnitude and a direction, but with tensors we also have on which face, on which side of this crystal structure the forces are operating. So this type of structures actually takes place, and when we study those crystals, if we extend them to these and further extend them to these actually you see that the hexagonal and the what you call the body centered, and then the simple all those face centered, etc., are very complex kind of shapes, which geometrical shapes which happen. So in order to know those things we need tensors, because we need to know really where the stress and strain is happening. So the origin actually started from studying the tensors, studying the crystals. So we now know the coin of the term, we know the relativistic part, why it is heavily dependent, the Einstein field equation, and the origin of the tensors historically. The big question that comes is that what kind of mathematics you need to know in order to learn tensors. And so these are the many faces and directions, and that is what is the next part of our video. We will quickly understand and then evaluate or re-evaluate ourselves that whether we know the prerequisites for learning tensors or not. Now the first thing which comes up is that linear algebra, which is a must, which I have already explained. So you come sequentially. In the second video we have learned linear algebra, so this will be required for vectors, matrices, etc., and the level would be, you can know, from intermediate to advanced. PDEs we have already covered in the first part of the video, and thanks to you for watching and putting up the comments. So multivariable calculus definitely is required in order to learn tensors, and it can also vary from intermediate to advanced. The second thing would be vector calculus. Yes, you need to know the gradients, curls, divergence, the Laplacians, etc., and for this you need the PDEs, so all are quite related, and you need to have an understanding of intermediate to advanced. Now these are which are optional, that means you can just skip. Non-Euclidean geometry is something which actually gives you an understanding that how these surfaces evolved, and how the non-Euclidean geometry is the place where the tensors actually take place. So you can just have an introductory understanding, but again it is not, because I'm making a video, I thought to give you a complete better understanding. And then comes what is called differential geometry. This is also optional, but most of the differential geometry books you will see will have a clear understanding of tensors, so it is something which you can skip. And finally abstract algebra, although some advanced features of tensors include abstract algebra, so that would be introductory and you can skip on that part also. So from here what we can understand, vector calculus, linear algebra, and partial differential equations, these three things are good enough in order to make our understanding of tensor calculus. Now we told that when things change from one direction to another, when vector transformation change takes place, we need to register them, we need to measure them. So that makes our question next is that how tensors are unique. I mean to say, why should we take tensor, why they are so important, and what makes them unique. Coming up into the next part of the video, I will just show you some geometric understanding so that things become clear. So here is a flat space where we are drawing a vector A, and we are measuring the component of the vector as AY along the y-axis and AX along the x-axis. Now what if we transform this flat space into what is called a curved space? So we plot the original Euclidean flat space, and then we take a curved space where the x is measured as x prime and y is measured as y prime. So in that case the vector obviously remains the same, but the components of the vector, as you can see, a prime x and a prime y, changes. So what happens is that a prime x is longer, a prime y is also longer, however a remains invariant. So that actually brings the beauty of the tensor. As you can see that the measurement of the vectors should be invariant, however the components of the vectors or the entire transformation takes place. Let us see another example where we get a kind of a static frame like this. Don't worry about this G part, I will come to that later. And if we rotate that axis from x to x prime and y to y prime, so here you see the original ax axis and the original ay axis, and this is the ax and ay. Now when I rotate it, this becomes a prime x and this becomes a prime y. Evidently right on the screen you can see that a prime y is shorter than ay. So here you can see a prime x becomes bigger and a prime y becomes shorter. And in order to register those things, what we need is a tensor, and that is what the role of the metric tensor is, and I will explain to you. So G00, G01, these are 4x4 components of the metric tensor, which is actually registering those changes so that the main vector does not change and we can efficiently measure that. So this would be a repetition which I won't like to repeat because it is coming sequentially. So I just thought to mention that in a rotated frame of axis and in a non-rotated frame of axis, how things happen. Here also the person is throwing the same ball and it is extended. So events are happening, but the events will be measured in the same way irrespective of the frames of reference. So the line gets extended in an oblate spheroid, and as Einstein has rightly quoted up to this. Now we understand the origin of tensors and I meant to say how the tensors are unique, etc. But now the question is that how it is related to relativity. I mean to say, obviously we are learning general theory of relativity. What is the role of tensors in general relativity? Obviously it is measurement, but let us take a quick example and make you understand. So in a flat surface, if I'm drawing a straight line like this and then I get a curved surface, when I'm drawing a same line, it will become curved. So what will happen is that evidently the distance formula or maybe the Pythagoras theorem or whatsoever, this won't work out. This is okay here, but this won't work out. And for that only we need a tensor component. Why? Because we need to define and compute length of curves on manifold, infinitesimal distances on the manifold, and we need tangent vectors. So the basic idea is the same, that the entire measurement, entire formula, etc. is going to change. And this distance formula, or we can say the Euclidean metric, is not going to work out. And that is why we need tensors. So here what we call it is invariant measurement under coordinate transformation. So even this coordinate transformation actually takes place. The metric tensor will take into account these transformation changes, and it will describe how the distance is measured, and it is used by turning specific coordinates that you use. And as you see, that metric tensor is that G part which we learned in Einstein field equation. Same happens with what we call the measuring the stress energy momentum tensor. That means this is a tensor, or this is a mathematical object which takes into account many things. The first part would be what is called the energy density. We will come to that part later. The second one is called the energy flux. This is the mu nu, that is the space-time direction, that means 3 length and 1 time, which consists of this 4 momentum is considered. This is the momentum density, and this is the shear stress, and this is the pressure. So what I'm trying to tell is that all those things, shear stress, pressure, energy flux, energy density, momentum density, these are all mathematical terms. These are all things which needs to be calculated. But how can we calculate in a curved space-time? So all these components T00, T01 actually denote something similar to that of an Euclidean space. And that is why we form that tensor. Now if I try to make things easy, let us discard this index kind of a matrix, and I will show it in simple English. So this is how it happens. So T is the time, X, Y, Z would be the spatial, and this is the temporal axis. So what we get is energy density, energy flux, and so on. So this is the energy density. What does that mean? It means that energy is responsible obviously for the curvature of space-time, because Einstein has shown us that E equal to mc square. So energy and mass. So if mass is causing a curvature, so will be the energy. Then it comes to the pressure part, which is actually a source, because if you're squeezing something, it is acting as a pressure. And then we get what is called an energy flux. That is the flow of energy which causes the curvature. So again, if I go back here, you can see the same things. But the same things are now made in an easier fashion in this kind of a table, where things are falling easily. And then we come to this part, which is called the momentum density. That means the energy and momentum actually represents how this flows. So I need to define later mathematically what is called a momentum density. So all these components are in a kind of a matrix. So now you see that linear algebra, tensors, how they are related. And that is why I made the video on linear algebra first, and now I'm coming to the matrix part, tensors part. So energy plus momentum plus pressure plus stress actually makes up the entire curvature. So this is one part of the tensors and general relativity. This is one part. This is stress energy momentum tensor, how it comprises and how the coordinate transformations are important. Now there are some mathematical concepts which I will quickly and easily define, but if you're not getting up to the point, then don't worry, I will explain it in the later part of the video, but that would again require a separate video to measure, to tell. Now there is something which is called a covariant derivative. I will come to that part later. So it is denoted by this nabla sign, Greek nabla sign. So you can just take it into consideration that it is basically an extension or generalization of the general derivative of calculus. So covariant derivatives are used to define the laws of physics in curved space-time. So for a vector field V nu, the covariant derivatives is given as this. Don't worry, these are Christoffel symbols, a little bit complicated. We will come to that part later. So covariant derivative is an extension of the normal derivative, and it is used in curved spacetime. So it is a kind which is related to tensors. Another very important thing which I have expressed in other videos, I will show you the video now. Ricci tensor and Ricci scalar. These are actually related in some way but there are other ways of writing the indices. So what it does is that the Ricci tensor, as I told you, it is a contraction of the Riemann tensor and the Ricci scalar. And it is a further contraction of the Ricci tensor. So the Ricci tensor and the scalar describes how the volume deformation happens, the referential volume. I will just show you a quick diagram, you will understand. Look into this. So you see the first one where the geodesic is the straight, so the ball moves in the straight line. So Ricci tensor is, or Ricci is 0, Ricci curvature is 0. On the left hand side you can see this, the geodesics are converging. And the ball is also shrinking. So the Ricci curvature is positive because it is shrinking. And on the right hand side, you see you are diverging. That means the Ricci curvature is less. That means Ricci curvature is less than 0. So this is how actually I would say the tensors or Ricci curvature actually more or less geometrically on a very rough way they measure things. And if you really want to make things much difficult for you and you want to learn, look into this video. This is general relativity made almost 2 years back, but you can look into this. This has got all the components which I have described. Go for the revised and edited because this is much clearer to understand. Now having said that, you understand that tensors are not to give you more tension. Tensors are something which are going to make your life easy. I will show you a very quick example how tensors make our life easy. Now consider this, the Einstein field equation, where we're just measuring this one, the Ricci part. Now you know that this Ricci part has got actually 16 components, and it looks like this, 0, 0, 0, 1, 4 by 4. Due to the symmetric nature, we have discarded the 6 components, but also this T looks like this. Isn't it too big and monstrous? So if I have to write just for this R all the 6 components, you understand how big the equation will become. It will be something like R00 minus half G00, then R01 minus half G00, then R33, and so on and so on and so on. Because G is also 4 by 4. So in order to make things easier, we just like this, where we use the R as the notation mu nu, and we are just framing it in a tensorial notation. So really that makes life easy. Also one important part is that Ricci tensor is symmetric. Now I will come to what actually geometrically symmetric means, because once you take a parallel transport along the clockwise and anti-clockwise, it is the same. I will come to that part later. But for the timing, let us understand that mu nu and nu mu, when you swap the indices, it will be the same. Why? Because it has only 10 of the 16 components which are independent. And how we can show, you see this part, then we cancel off all this, and what ultimately remains is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these are the independent components. So the off diagonal components get cancelled out, and again the linear algebra comes up, and we just get the 10 components. And same happens with the stress energy momentum tensor and the metric tensor. So you can very well understand that how tensors are reducing those huge equations which would have been otherwise very tedious to write. We come to the next part, which I will just take a little bit time quickly to explain, because this is important, what is called tensors and covariant derivative. Don't worry, I will make a video later on covariant derivative. It's a little bit technical. So in a Euclidean space, the derivative of a function is straightforward. How? So the covariant derivative is basically an extension of the partial derivative. So it becomes compatible with the geometric structure of the space-time. So in Euclidean space, with a vector field v nu, and with take a kind of a coordinate system x mu, we take the partial derivative as del mu v nu. Now in curved space-time, definitely it doesn't happen, and the partial derivative is not taking place in the right form. So how do we transform? We introduce this component, nabla mu followed by v nu. And this nabla is basically the covariant derivative, which takes into account what is called the curvature of the space. Let me show you with a quick example of that. Here is the equation. So here you see this part is basically the covariant derivative of the vector in the direction, or vector means in the direction v nu. Then you see this part, this is the general partial derivative with respect to x mu, and this is what is called the Christoffel symbols, which is a kind of a connection term. We'll come to that part later. And we can see this in a very simple example. Let us see that. So if I get a kind of a two-dimensional space with x and y coordinates, and we have a vector field v with components vx and vy, then the covariant derivative vx with respect to x would be simply this. And the covariant derivative with vx with respect to y would be this. And you can see these x, which is at the indices, lower and upper, it happens around here also. And this is how the Christoffel symbols behave. So don't worry if you don't understand, this is a little bit technical, I will take time. So what we understand here from here is this one, that covariant derivative is a very crucial concept in tensor calculus, because it allows for differentiation in a curved space-time and reserve what is called the tensorial properties. Again, a wrong English, I should say tensor-like properties, and it generalizes the notion of derivative, because derivative won't work in a curved space-time. So ultimately the bottom line, what Einstein told, we are sticking to that the physical laws remain consistent and invariant under coordinate transformation. Now, in order to learn all those covariant derivatives and then contravariant, covariant tensors, all those indices, definitely you need resources. We will come to the resources, but first I would like to show some of the online resources which you can very quickly go, and which is related to this video also. You can first go to this video of mine, which is almost 2 years back, metric tensor and general relativity. You will understand a complete understanding of metric tensor and its derivation. You can also look into part 2 of what is a tensor. This is a good video where I've explained very clearly, and these two videos are also good. It is a little bit, in this year I have done it, Tensor Fundamentals Lesson 1 and Lesson 2. There is a whole list of vectors and tensors in my Physics for Students playlist, vectors and tensors, and you can watch it one by one. And if you want to understand tensors exclusively in terms of general theory of relativity, you can go to lesson number 20, which is there in the playlist of general relativity. We come to the next part, and what is called is the books on tensor calculus. Now I'm going to show you a few books. It is not that you have to learn all of them, purchase all of them, but if I give you more options, you will get a better understanding of things. You will understand things better, which one to go for. The first book is very famous, very easy and very simple. It is called Daniel Fleisch, A Student's Guide to Vectors and Tensors. And this is Professor Daniel Fleisch, 78% customer reviews in Amazon. Well, it's good enough. Now, I will also show you the overall content. And because you are learning tensors, and this is related to general relativity, you will see that these, content also covers a lot of general relativity part. We just talked about metric tensor, it covers it. You see again tensor derivative, Christoffel symbol, covariant differentiation, Riemann curvature tensor. So I'm saying it just starts covering general relativity part also, and that's the good news. Here also you see from page 197 to 105 we cover a lot of covariant, contravariant components, basis. This is an excellent book. This is my review of this book. This is one of the best self-complete book. You really don't need to go for any other book. A lot of subscribers has later given me a WhatsApp message telling that this is a very good book and we really learned it easy. It's a very easy introduction. It offers a clear explanation. Nothing is left unsaid. So it's a great introduction, great book, focuses on the basis of vectors. Step by step it builds up and the text is very clear. Now from this book, obviously it won't be very rigorous mathematics. We need to go on a little bit onto the mathematics, and for that the famous G.E. Hayes book on vector and tensor analysis is good. Again, the customer review is 68%, which is fair enough. Also, you will see this book contains certain areas into tensor calculus and general relativity. As you see, differential geometry, a little bit of the Sennett-Ferrer problem, the curvature and torsion, these things are covered over there. But most importantly, you will see that the book starts with an introduction. It nicely covers what are the vector operations, scalar vector, and then it moves into application of geometry, and then it further moves into vectors to mechanics. So again, self-complete book, step by step, it covers all. I cannot cover everything about the book. It would take a long time and it would be boring. So here again you can see that the curvilinear coordinates, the expression in terms of the Laplacian, the line integrals, Stokes theorem, Green's theorem, which is a part of the integration, is also covered, and then comes the tensor analysis, and you can see at the bottom of the screen covariant tensors, vectors, metric tensor, again it is being covered. So you will learn a good part of that. So this is my, okay, so we also have got tensor analysis, etc. And yes, so this I have circled because covariant, contravariant, so whatever the most crucial part is already being covered. So if I take this is, yes, it is an excellent introductory level text for undergrad levels, and the brief statement of Serre-Frenet problems for lines and spaces is nice because it goes through that and is highly recommended for undergrad level as an introduction to the subject. Next comes another book which is quite rigorous in terms of understanding the mathematics, Borisenko and Tarapov's Vector and Tensor Analysis with Applications. 74% of customer reviews. Here comes a quick overall content of that. So you see vector algebra, then it comes into basis and transformation. I think this is even better. It goes to the grassroots level. Then scalar product, vector product. Then you can see on part 2 it starts with the tensor concept, and then it comes terms with invariance of tensor equations and so on. It's quite a good book. I mean to say it's fairly mathematical and gives you a complete understanding. So here you can see the lot of pages have been covered in vector tensor algebra, and then you can see on 191 and so on the Ricci's theorem, the Christoffel symbols, so everything is covered. Most importantly, as you can see here, the book covers a lot of diagrams, and this gives us a fair good idea in order to visualize things. So it's an excellent book to clear up your ideas. Here I have written that is very concise and focused because it covers areas like covariant derivative, metric tensor, geodesics, etc. And the section it devotes to integral theorems look more in touch with the current trends in mathematics than most of the classical texts. So yes, it is definitely a good book, and it will also give you an application. Remember, it's a translation from the Russian part, obviously. Now these are the mathematical part of tensors which we have learned. Now what about that we learned the tensor from the physics point of view, because we are learning relativity, which is integral part of physics. So here is a book which is called Tensor Calculus of Physics, and this is written by Dwight E. Neuenschwander. I'm so sorry for my horrible German pronunciation. 78% 5-star, good enough. And this is Professor Neuenschwander. This book basically takes into account the physics part. So you can see that Euclidean vectors, Euclidean gradient, then what is the theory of relativity, then inertia tensor, obviously because this is the book on tensor calculus for physics, so it will take into account the physics parts definitely. And then you can see the electromagnetic stress tensor, the eigenvalues, eigenvectors, the upper and lower indices, why it happens, the relative motion. So everything will be in relation to physics. And I think this is a good point to do, because ultimately the objective would be to learn physics, and in order to see how the physics part is also taking into consideration. So if I take the overall idea of this book, it also covers derivative of tensors and the divergence and curl. That means the vector calculus part is also taken. Then you can see what is curvature. Here you see Riemann tensor, beautiful, covariant electrodynamics, tangent spaces, charts and manifold. That means a part of differential geometry is also being covered. Yes, I would say tensors and manifolds, derivatives, bases, etc. are all covered. So overall it is an excellent book, but remember that it is not as lucid as Daniel Fleisch's Student's Guide to Vectors and Tensors. It's not that clear. And it is an excellent book because it will give you the mathematics that you need to know. Now, after going through Tarapov and Neuschwander and GEA and then Fleisch, we come to a very popular but a very good book by an Indian author, Prasun Kumar Naik. And I actually contacted him. He's a teacher in applied physics and mathematics in India. And this book, Tensor Calculus and Differential Geometry, this I would say is an amazing book. Now, why I'm calling it amazing? Because not only you will learn tensor calculus, but things which are connected with tensor calculus and differential geometry, that will also be covered in a nice way. It is magical that you will never understand, but at the end of this book, you will also learn a lot of differential geometry. So here you can see it starts with the Riemannian metric, and almost everything related to the mathematics of general relativity is already covered. So this part will cover the Riemannian metric. As you can see, Christoffel symbols already started from page number 140. And then you see here the Christoffel symbols and covariant differentiation. And this is what I was talking about, that how it is important. So the Riemannian geometry is also being covered. The space constant, zero curvature and Einstein tensor. So I call this book amazing because you're learning tensor calculus, you're learning Einstein's field equations, and you're also learning differential geometry. So all of them taken together and a very clear manner. I won't say it is rigorous, but yes, it is mathematical, but it is an amazing book. So here you can see again relativistic mechanics, which is invariance of space, invariance of time. Again, it is covering Minkowski space, that is a part of the special theory of relativity, generalized relativity, planetary motions, Einstein universe. So all these things are covered. So lot of physics, lot of relativity, lot of differential geometry, and obviously tensor calculus. So what I can say is this: the book contains numerous problems which you can try out, very clear and lucid, and many more advanced topics are discussed in a very lucid manner. So overall, it is a very good book. The next book would be, yes, it is also what I would say mathematical in nature. It is called Robert C. Ward's Introduction to Vector and Tensor Analysis. 72% 5-star. This is Professor Robert. But most importantly, you will see again the book will start with framing you from the basics. So the historical summary will be given. Then the general Cartesian coordinates, that means the inner product, etc., which is there in linear algebra, that will be given. Then Professor Ward would move into geometry of spaces and curves, kinematics, etc. Then it would cover partial differentiation and associated concepts. That means what? That means that the associated concepts which are required before you jump into tensors are also being covered. You can see chapter 5 covers a lot of Riemannian geometry, geodesics, Levi-Civita symbol, curvature tensor. That is excellent. So I can say that overall it is a very good book. Yes, explanations rigorous and clear. There are no confusing errors. As a matter of fact, no errors, because some of the book do have errors, and the exercises are well thought. So the best element is that the applications in physics are utilized in almost each and every chapter. Now, having understood so many and taken into account the reviews of so many books, you might have a question that what is the order and how will I read that? What is the order in reading those books, and how to start with that? And that is what coming in the final part and the most important part, in which order you will be reading them. So taking into account all those 6 books, first I would say start with Vectors and Tensor by Daniel Fleisch. That would give you an intuitive, basic, simple, yet a very logical and a clear understanding of vectors and tensors. Then move into Prasun Kumar Naik's book, because that would be related to the thing that you have learned, but on a much more rigorous mathematical proofs, and those things of tensors you will now start relating to physics and differential geometry. Immediately after getting an intuitive idea as well as a mathematical idea, you need to look into the physics part. So Neuschwander's tensor calculus for physics would be a good one. Then 4 and 5 would be okay. I mean to say you can go, you cannot go, because these are extensions of the learning. But yes, it is much more mathematical, starting from the base, lot of examples, great. And finally, you can go into Introduction of Vector and Tensor Analysis by Robert C. Ward. So that completes our journey today, that how tensors evolve, what is tensor, how tensors are related, and what is the role of tensor in terms of general relativity, how will you learn sequential books, online resources, etc. So that's it for today's video. I'm thankful for those who have really taken up time to watch this video, because I'm continuing with this series very seriously. If you have liked the video, please click on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can write to my email ID at this, and you can contact at my email ID. You can also subscribe to my other channel, which I'm not putting up too much videos. That's true. That is General Relativity Explained. And you can follow me on my Facebook, LinkedIn, Instagram, and Twitter accounts. So Physics for Students will be back, because this series has got few more videos to come up. So please do subscribe, please do comment, and let me know how this series is going. And there will be more other videos on Physics for Students. And stay tuned for upcoming more surprises from this channel. Thank you very much.